thank you, Lee and Urbasi, for the great talk. So my question is to Lee, and this is corresponding to the slide which has a title, Causally Non-Separable Process. Go beyond the circuit model. Yeah, that one. Yeah. In that slide, the last part that you have shown, that should be a tensor product of U1 and U2? Because I understand that I think U1 and U2 must be single qubit gates, right?
Yeah, that's right. They're single qubit gates, but there shouldn't necessarily be no, because they're still acting on the target system. So they're both acting on one system.
Okay, if we go one by one, the first one is a time evolving state. Yeah. The first one. Yeah. I think that's the qubit line, right?
Yeah, exactly. That's just a standard quantum circuit. So that's U1 before U2.
So state evolves acted by U1 and then further acted by U2.
So there the state is, okay, actually, maybe I see your confusion. So the state of the first one should be U2, U1 psi. And the state of the second one would be U2, U1 psi. The last one there is actually, so it is then meant to be a superposition of both of those states. So the idea would be U1, U2 plus U2, U1 acting on psi.
Okay, so it's going to be a 4x4 matrix.
No, it depends on the, no, it should still be a 2x2 matrix.
Yeah, 2x2 matrix.
But I think in,
oh yeah, that's right.
I don't know if I have it written out explicitly. Yeah, so explicitly though, for the quantum switch, you also have the control degree of freedom. Okay, thank you.
Okay, no, so the moment I saw that, I was somehow under the impression that it's U1 tensor U2.
Yeah, no, so, now it's, where did it go? So this is a state here. This is a full state. What I wrote before was just kind of leading up to the actual quantum switch state.
So now it's clear because it should be acting on a single state. Single
that's
qubit.
Right. Yeah. I mean, in general, this could be, it doesn't have to be a single qubit, but it's just one system. Like psi can, in principle, be an arbitrary dimension, as can U1 and U2. But typically, it's taken to be a single qubit.
And so this U1 will essentially be a special unitary SU2 operator?
Exactly. Yeah, so in almost all of the experiments to date, it's usually taken to be a single qubit, and then U1 and U2 are SU2s.
And so when you want a certain kind of experimental feasibility, you will fine-tune the rotational angles?
Yeah, exactly. So for like some of the first tests, we're trying to test this idea here, where we want to just have U1 and U2 and see if they commute or anti-commute. So for example, the easiest, the gates that make sense to show the symmetry are the poly gates, because they have nice commuting and anti-commuting relationships. So then U1 and U2 are just taken from the polys and then act on a single qubit.
Okay, thank you.
Yeah.
Thanks. Can you please tell where are you from?
My name is Vijay Krishnan. I'm from JNCASR, Bangalore.
Thank you.
Yeah.
Okay, so our next question is from Arijit Chatterjee. Again, you please introduce yourself before you ask the question.
Hi, I'm Arijit Chatterjee from ISER Pune. My question is also based on this slide only, where you are using this control qubit to implement this indefinite causal order. So this first part I understand, that when it is 0, you are applying U2 first and then U1. When it's 1, then you are doing the other way and putting it in a superposition. But then in the end, when you put it in a superposition and then apply, so these are like, then you are applying controlled unitaries, right? Which should result a correlated state.
Yeah, I mean, you can think about this as a controlled unitary, where essentially you're controlling. So if the control qubit is 0, then the unitary you apply is U2, U1, and if it's 1, you apply U1, U2.
Yeah, so now if I stick to this state, and now if I trace out the control, then the reduced density matrix of the system is a statistical mixture of application of U2, U1 or U1, U2.
Yeah.
But So then any future measurement of the system is completely determined by the reduced state of the density matrix of the system only.
Yeah.
So then instead of using this control qubit, if I choose from a classical probability distribution, I say with probability half I apply U1, U2, probability half I apply U2, U1, I would have ended up in the same ensemble of the system. So then I'm not understanding what's the role this quantum superposition of the control is playing here.
Right, so you could do it that way. But so for this protocol though, we actually do it the other way around essentially. We disregard the system state and measure the control state.
Yeah, that's right, yeah.
So if you wanted to do what you're proposing, just looking at the system qubit, that would be kind of equivalent to trying to stick with a quantum circuit?
No, that's equivalent to...
well, flipping a coin and doing one state or the other.
Yeah.
And I think you're right. Essentially, you could tune the state of the control qubit in this case, and then trace it out, and then realize some mixture of whatever mixture you like of U2, U1 psi and U1, U2 psi. But that doesn't lead to the advantage. Yeah. So you could do that, and it would be equivalent from what you get on the system qubit. Yeah. But then you wouldn't be able to play this game, because playing this particular game requires you to look at the target qubit.
Oh, okay.
I think
Manik has a question. Follow-up.
Or he wants to clarify, maybe.
Yeah.
Yeah, if you just trace out the control, it will be just what you said, it will be a convex mixture of these two things. What you have to do measurement on control.
Right.
Yeah.
You have to do plus minus basis measurement on the control, and then accordingly you have to look into the target state. Yeah, that you take from plus control things. If control is plus, you are getting that. Yeah, because what he discussed, your task is you are only allowed to use the unitary only one times, and the promise is whether they are unitary, they are commutating or anti-commuting, that you have to decide. If you do the measurement on the control on plus minus basis, that using one use of the gate, one query of the unitary gate, you can do that. That is the advantage. And regarding this other things, what you said, the tensor product, you see it is a space-like separated. Yeah, space-like is a tensor product is a space-like separated operation of U1, U2.
Surajit, does that clear your confusion?
Yeah, I'm fine.
Sorry, Arijit.
Right?
Sorry. Okay, so next up is Surajit Shaha. You may please introduce yourself and ask your question.
Okay, I'm Surajit Saha from Calcutta University. My first question is, what is the interpretation of indefinite causal order from the Bohmian point of view? Does Bohmian trajectory supports indefinite causal order?
I haven't thought about that at all. But, I mean, Bohmian mechanics reproduces all quantum mechanical predictions, so it should also occur in Bohmian theory, at least the quantum switch. I don't know what Bohmian mechanics would do when you try to use it to violate these causal inequalities. Because these causal inequalities, they come up from these process matrices, which are kind of, which aren't really like standard tools, and we're not even sure if they're really physically implementable. So I don't know if you could really derive Bohmian trajectories that would show a violation of the causal inequality. This game I introduced at the beginning. I don't think you would be able to, but I could be wrong.
Okay. My next question is for Professor Urbasi Sinha.
We'll come back to the next question. So Professor Home has a comment to make. So somebody give the microphone. No, he will give.
Okay.
To derive the inequalities, because the ingredient you need to some assumption about that matrix. That
sorry to do
what are the essential ingredients for deriving those inequalities? If you just restate, I will. ask
Yeah,
a
so
specific
to derive the causal inequalities, the main assumption is that, so there's some process which connects Alice and Bob's lab.
So that is a theory-independent assumption. I mean, I'm trying to compare with this, with whether it is theory-independent up to what extent.
Yeah, so
quantum
the
input
derivation
comes
of the causal inequalities themselves are theory-independent. So they're the assumptions are that, you know, Alice and Bob can freely choose their measurement settings, that they can act on the system that's shared between their lab once and only once, and then I think that's essentially it. And that there's a fixed causal order between them. So if those three assumptions hold, then you can derive the inequalities.
So all the assumptions are theory independent.
The assumptions for setting the limits are theory independent.
Yeah.
And then, but there are also some assumptions which go into showing that quantum mechanics can violate the causal inequalities.
So that is using quantum.
That's using quantum mechanics, yeah,
So
to show the violation.
So,
Yeah.
so in that sense, Bohmian mechanics is equivalent to operational and quantum mechanics. So whatever you get from, so in that sense, it should
it's
violate.
not specific. So what they assume when they show that, when they say that quantum processes can violate the causal inequalities, they assume that quantum mechanics holds locally within the two labs, but and that all probabilities are normalized, no negative probabilities, and so on. But they don't make assumptions on, so that's the only assumptions they make on the process that connects the labs. Oh, and that the parties again act once and only once. But there's no other quantum stuff that really goes into these process matrices that are connecting Alice and Bob. So I don't know for sure that you would be able to derive Bohmian mechanics for that.
No, not Bohmian. It is independent of theory, so it should hold good in any. And Bohmian is equivalent to quantum mechanics from the formalism point of view.
But to derive the violation, though, there might be a slight extension of quantum mechanics. What goes into the deriving the violation is that Alice and Bob have local quantum. That quantum mechanics holds locally for Alice and Bob.
To derive quantum violation of Bell inequality, you need the formalism of quantum, the way you compute the spin correlation.
But there's an additional ingredient that goes into violating the causal inequalities.
Okay, what is that additional?
We're not entirely sure. It's just that there's some process that connects Alice and Bob.
So that is outside the formalism.
And that could be outside of the formalism of quantum theory.
Okay, that's the gray part.
Thanks, Professor Holmes. So your next question?
Okay, my next question is,
I don't know if I overstated
for
that.
Professor Urbasi Sinha. Ma'am, can you achieve postponed compensation Hong-Mendel effect using classical pulse?
Sorry, what was the adjective?
Postponed compensation Hong-Mendel effect, where the two photons cannot arrive simultaneously at the beam splitter. There is some delay. Actually,
Postpone, so this is an interesting term. Postpone compensation. So it's not post, it's postpone compensation. So you're saying that you have a single photon which has appeared at the beam splitter, and another photon has appeared at a later time.
Delay. There is a
so
delay.
Of course, these are then perfectly distinguishable photons.
No, they are entangled photon.
No, there's nothing to do with entanglement in Hong-Mendel, right? So maybe there was a bit of a confusion. So we have two single photons incident on the two ports of the beam splitter, one this way and one that way. These photons are not necessarily entangled. They need not be entangled at all.
Yes.
So you have a photon 1 and another 1, so two Fock states. And the idea of the 2, 0 minus 0, 2 comes up. If you see the algebra, this perfect cancellation will only happen if both these photons are perfectly indistinguishable in all degrees of freedom. And what you have just said by that interesting term, which of course I will have to remember, is that this one photon has arrived at time t1 and the other one was delayed and it arrived at time t2, which makes them distinguishable in their arrival time.
After the after beam splitter, this delay has been postponed, and one can observe the two photon interference.
So these two photons, they arrived at the same time or not?
No.
At the beam splitter to begin with.
To arrive at the detectors after the beam splitter.
So, but then what happened to the two photons before the beam splitter? Exactly. So this was so when you are talking about the the delay, was the delay before the beam splitter or after the beam splitter?
Before. but after that delay has been compensated.
So I think he wants them to arrive at different
You want to
times.
make
Right.
it just
And then
one second?
afterwards,
Afterwards, compensate. But then that won't work, right? Because if they have arrived at different times at the beam splitter, then themselves they have become distinguishable.
Yeah, so it's work only indistinguishable.
Bunching is possible. So then, so this is what you're saying, that these two photons, they have arrived at different times at the beam splitter, but then at the detector, the photon which arrived early is delayed to arrive at the same time as the other photon which arrived late.
Bunching
Yeah.
is a possibility.
Bunching is a possibility, is what Manik is saying, that there is an experiment. Then, I mean,
Yeah.
it's like two wrongs making a right.
Girish, can you just tell
Yeah,
that?
you wanted to make a comment?
Girish wants to say. Postpone compensation. I like it.
Yeah, so I just have a comment which can probably clarify this. So there are two different contexts in which the HOM effect is seen. So one is with entangled photons, which is the original context of the Hongo-Mandel experiment. And there...
That is spatial.
Yeah, so but I mean...
Just to clarify that, they actually went on to show, and so this was in fact the Ghosh-Mandel experiment made an issue, actually clarified that even better, where they said that, if one of the photons is arriving at a specific location,
Right.
then the thing will happen only at a certain corresponding location, making use of the inherent spatial entanglement that is there in down conversion.
Correct.
Yeah, it's not necessary, it doesn't require polarization entanglement.
Yeah, it does not require polarization entanglement. That's absolutely correct. But the experiment was done with entangled photons, and there was a paper in 1996 from Pittman. This was a group from University of Maryland, Baltimore County. So what they said was that, look, this bunching interpretation of the Hongo-Mandel experiment is not quite right, because you don't strictly require the two photons to arrive at the beam splitter at the same time. So what you can do is delay one of the photons, and then sort of introduce another delay to the other photon after the beam splitter, such that they arrive in coincidence. And the aim of that experiment was to show that, look, it's not really the two photons which are interfering with each other. It is actually a two photon as a combined system which is interfering at two different paths. So, that was the kind of thing. So you basically compensate any path length difference, and it just works. So I think that will be that's the basis of his question, I believe.
You want to say something? I'm saying but.
I just can't picture how that works. If all you're doing is, because you apply the transformation at the beam splitter, and I don't see how detecting the photons
Yeah, so
compensate, unless coming in you have some temporal correlations or something that.
So when you apply the transformation of the beam splitter, you assume that the two photons are actually indistinguishable in all the modes, and then that bunching interpretation holds fine. So in that case, you certainly require both the photons to arrive at the beam splitter at the same time. But if you're doing the experiment with entangled photons, you can actually think of Hongo-Mandel effect as a two-photon interference effect, and in that case, it's not really required that the two photons actually arrive at the same time.
So then there's some entanglement in timing degrees of freedom of the photons before the beam splitter.
Yeah, so they don't need to arrive at the beam splitter at the same time, but then since they have to get detected in coincidence, you have to compensate for the delay.
I think the point that was just made is important then, that there must be some entanglement in the time degree of freedom.
That's correct.
Which is what is harnessed, because they would remain entangled, even if, you sort of play around and make one appear later, that entanglement holds, and then you can post-compensate and sort of make it seem like nothing really happened.
So I would see it as a variation of the Franzen experiment.
Sure.
I mean,
but
it's a temporal
but then to
interference
answer
experiment.
the question, so this is a special case, in which this would work, right? Like otherwise, of course, if these two photons did not share that initial correlation, then I don't see how this would bunching would appear, because this is a special case, and perhaps the experiment also deals with this special. So I would say this is a little reminiscent of what we also said, that in certain scenarios you can mimic the dip even without entanglement or photons. So I mean, so these are all, of course, deviations from the original thought.
And another interesting aspect is that you can actually make the dip go to a hump as well.
Hold it a little away. Yes. Thank you.
Yeah, sorry, I was just adding that you can actually change the phase of the interference experiment in such a way that the dip turns into a hump.
That you can do.
So that's also something
also
that can
you
be done. Yeah.
But of course, yeah, these are tricks one can play. But then if these two guys did not share that initial correlation, then of course it won't.
Yeah, I don't think it will work with
without that initial entanglement. Yeah.
Right.
Okay.
Okay.
So you
Thank
have
you.
any other questions? Otherwise, we'll move on. So next up is Tushar. Yeah, Tushar there. Can you give him the microphone?
Hello. So
you want to ask before him? Or no? Yeah. So can you introduce yourself and ask?
yeah. So first of all, I would like to thank both Professor Urbasi Sinha and Professor Lee for their nice talks. So I am Tushar from IIT Jodhpur, first year PhD students. So my first question is to Professor Urbasi Sinha. Can you go to that Feynman path integral slide?
So in the context of higher order interference?
I have to get her. I mean, there are two slides, but you will tell us when to stop. We go on, because now we are doing only the bond rule. Now, this?
Yeah, this one.
Yeah.
This is the, yeah.
So my first question is, how did you incorporate that non-classical parts?
You
Like
have
kappa.
to click one more button for the purple line.
Yeah.
No?
Next slide or this slide? Or
No, there, if you click the button, then that, no,
You can click here too.
Acha, it
you
doesn't
can
need.
also use your...
It doesn't need. Ported slide. I think the non-classical path is
Yeah,
not there in this
non-classical
slide.
parts. Oh yeah, sorry.
But this one,
so this
perhaps.
one,
This
yeah.
one.
the one.
So what was the question about it?
So how did you incorporate it experimentally, that purple lines?
Oh,
Like
that's
how-
so. This is not an experiment. So this was the theory, right? So in
Yeah.
what we did is, of course, in the theory we incorporated, all kinds of Feynman paths. So of course, and that is how we got the non-zero. In the experiment, of course, we did not need to do anything special for it. It naturally appears, right? That is the whole point. So if you open. And our experiment was not a slit experiment, it was a slot experiment, just a little bit of a detail. So instead of actually having 3 slits, we had 3 slots. So because it was easier to actually have these, because it was a macroscopic experiment, so that is a slight detail. So if you have them all open, and then of course if you, put barriers and close one or the other, that effect naturally comes in. No? You don't have to do anything.
Yeah, but you introduced the kappa parameter in
the kappa parameter.
Yeah,
so we have to do 8 experiments in order to get that kappa parameter. So one will be the 3 and then the various combinations of the 2s, then the 1s, and then one will be, in this case, we use the Babinet principle. So essentially we had one scenario in which everything was open, and in one scenario everything was closed. So in the slit experiment, everything closed gives you that thing, whereas in our case, all the background is elsewhere because it's a whole open field. So we use the reverse logic, but then anyway, that is the 0th parameter, the error probability. And so we had to do 8 experiments and add and subtract in the way the Sorkin parameter is defined. And so one detail which I could not say, which I should say now, is that this addition and subtraction gives us actually the epsilon parameter, as we call it. Then we have to normalize it. And so we normalize it with the sum of the 3 double slit terms, so the I2 terms, I2AB plus I2BC plus. So this was the normalization also used in the photonic experiment in 2010. And that is what gives you kappa. So there is, so the whole point is that you don't need to do anything to see the effect of the Feynman paths. The non-zero is that indication, but what we did is we did the complete simulation of the experiment and confirmed that our kappa as a function of detected position perfectly matches the theoretical
So the Sorkin parameter is epsilon or the normalized one?
The kappa, the Sorkin parameter was actually had 7 terms, right? Like, because Raphael Sorkin is, of course, a very well-known theorist. He doesn't do experiments. So he did not worry about the fact that when all the slits are closed, you can still measure something at the detector. So we introduced the 8th parameter to ensure that we were doing something right. And so that 8th parameter introduction made it different from the original Sorkin, and that's why we call it epsilon. Because whenever there is something experimental, it's a Greek symbol. And so from Sorkin parameter, it becomes epsilon. And then, of course, the normalized one we have to measure, because otherwise, how do we compare different experiments? because the epsilon quantity is going to be some term, but only when you compare it with the double slit, then it's like a triple versus double scenario. So you compare something which is the third order versus an expected sort of hoped non-zero versus an expected non-zero, because the denominator has to be non-zero. The other denominator we had used was the sum of all 8 terms, but then that leads to some of these weird false sort of peaks in the graph. So this was done after a lot of discussion and trial and error, that we compared the 3 versus 2.
I just wanted to add a little bit.
Yeah, please.
Can you also comment on that Boyd's paper that you referred to, that where they have shown enhancement of this kappa parameter using metallic slits?
Yeah. So see, what they had, of course, the original intention of their paper was to measure these, they call it exotic looped trajectories, which is what we call non-classical paths, but then, so it's the same thing. So, but then if you just do the experiment using, their experimental parameters, the geometric values of the slit width and interslit distance and all, is the same as the first science paper. So that would give you a kappa of the order of 10 to the minus 5, as I have also shown you in one of these slides, that, so this is a very difficult thing to measure, because the experimental errors in these experiments will sort of ensure that your zero itself is, let's say, 10 to the minus 2 or 3. So anything of the order below that will never be measured as a non-zero value. And so somehow you need to enhance this. So of course the way it was suggested, the enhancement without bringing in anything else would be to play around with the slit geometry. So, as I said, lambda to the 3 by 2 by d to the half w would do that. So if you increase lambda, which is what we ended up doing, we went to centimeter from nanometer, and then of course the commensurate. But what the Boyd group did is they stuck to the micron level slit. But then, of course, their kappa will not be measurable, because it's not like they would have.
They used a metallic surface.
They used a metallic surface, and so the metamaterial.
Enhancement in the near field.
In the near field, this enhancement happens, and I am sure you know the theory behind this. So they used, this theory of metamaterials, and that gold apparently has a very high nonlinearity parameter there. So at this, sort of where these things come together. There is an enhancement which is because of this material and not to do with the, the original intention of measuring non-classical paths. But then, any non-zeroness, is a non-zero kappa. And so theirs is a material enhanced non-zeroness.
Just enhances those loop trajectories.
Not enhances, no, it is a different kind of loop trajectory, because, it's sort of...
near field, so basically you have a longitudinal component in that sense.
Yeah, and so it essentially makes it seem like these contributions are larger than what they would originally be if this material was different. So it was a different way of enhancing them, yeah.
So my second question is...
So Manavendra, you wanted to make a comment now or later?
No, student. Okay, so my second question is, like Lee, you introduced POVM. Sorry, not POVM, weak measurements. So can we use these weak measurements to perform the POVMs, in which, like in POVMs, we just only get outcomes, not the state. We have no information about the state. So can we use this weak measurement to perform POVMs and still have information about the state, like state is not destroyed?
So I think it would depend really on the specific POVM you want to implement, but you don't necessarily need the weak measurement formalism for that. But I think just actually having this coupling, like using an ancilla system, so the von Neumann measurement idea, that should already be enough to implement some interesting POVMs. And but yeah, it would really depend on the specifics of the POVM. And I don't think you need the weak measurement, just the,
So weak measurement doesn't give any advantage for POVMs, for implementing for any POVMs, right?
In general, I would say no, but it would really depend on the specifics of what you want to do.
Okay, thanks.
Okay, thank you. So Manavendra, you wanted to make a comment, I think.
Since the context came, I wanted to ask a question to Lee. Because we know that so far all the quantum processes that we know, they don't violate this causal inequality, this ordered causal inequality. So, but you mentioned that there may be some possibility that such operations do not exist within the realm of quantum mechanics. Is there any proof on that part saying that, see, that if any violation is there, that means it has to be beyond quantum mechanics? Or vice versa, that there is some indication that within the realm of quantum mechanics we can find some process that violates causal inequality?
I don't know if there's such a general proof. So what people normally tend to do is these process matrices that connect the two labs, like I said, essentially all they require is that quantum mechanics holds locally for Alice and Bob, and then you can exchange quantum states somehow. And people have tried to introduce other notions of physicality. So for example, one thing, I think it was also from Chazlov's group, they introduced this notion of purifiable processes, essentially saying, you should be able to purify your process so that you can reverse it and still have a unitary transformation. So they introduced a notion of physicality, but it's not, it's just something they liked. It's not something that would necessarily apply. So I don't think anyone knows if there is a general statement of what is allowed in this context.
So among the assumptions, which one you think the most stringent one, or possibly the one which may not be incorporated or may not be allowed by quantum mechanics?
Well, I mean, there's just no assumptions made on what connects the two labs. So I think the assumptions that they make on the local labs are all very reasonable. But they don't say anything about, like I said, how you send a qubit from Alice's lab or a quantum system from Alice's labs to Bob's lab or vice versa, how those things are connected. So because of that, it doesn't call on quantum mechanics. It's possible that there are additional constraints that we need to put on those allowed process matrices. And as far as I know, there's no agreed set of constraints that we can add that we should add to make them physical. So it's kind of an open question as far as I know.
Okay, thank you.
Thanks, Manavendra. So next is Professor Singh. Please bring the microphone to us. Here.
So thank you to both the speakers for very interesting talks. Let me give a title to my question and a couple of minutes for a background, so bear with me. So the question which both of you can address, is there quantum interference in time? Related to some of the earlier. So when you talk of an indefinite causal order, I would like to make a spatial analogy that if you take points x and y on the real line, x is to the left of y, and x is also to the right of y. I want to make a superposition of both these locations, relative locations. To me, that means that I should start treating x and y as operators so that their eigenvalues can have relative locations. So in that same spirit, I would like to treat time also as an operator if you are talking of indefinite causal order. Which brings us to this question that there should be interference in time. It's like not only can a particle be in two places at the same time, it can be in two times at the same place. So one way some people have tried this, if you have a slit and a wave packet going through the slit, make an arrangement that the particle turns back into the slit. So before the tail of the wave packet leaves the slit, the head is back. So that's one way of saying this thing is at one place but at two times. And if there is an interference, you expect something like fringes in the energy bands. And some such experiments have been tried, but they haven't got attention. And the reason why I think it's very important to answer this question is relates to relativistic quantum mechanics. Like Stuckelberg in the 40s had a relativistic version of quantum mechanics in which time is an operator. And then other people followed it up that if that is so, there should be time interference. Also of interest for collapse models, if there's spontaneous collapse in time, then macroscopic systems will not show time interference because the superposition times will collapse very quickly. So now coming to my question, are you familiar with the history of this interference in time thing? And your experiment, which is very attractive, can you test for quantum interference in time? I think it's very pressing. It seems doable, and if someone can do it, we have a beyond quantum mechanics kind of thing. Thank you.
I don't know that I have a good answer to that. I mean, the first thing you said that you loop a wave packet around so that you interfere the head of the wave packet with the tail. I don't see any issue with implementing that experimentally.
Mm-hmm. Can you use a pulse or something like that?
Yeah, like you use some pulse. And I mean, there are other interference effects in time. Like if you take two pulses and overlap them into the same spatial mode, you'll see some interference fringes in time depending on the relative phases and so on. Actually, I think maybe even the question about the postponed Hongo-Mandel idea could also be viewed as interference in time in some way. So I don't see any reason why we can't do those types of experiments.
So would you say, suppose you go ahead and do that experiment, find the time interference in energy bands, would you go ahead and then make a statement that hence time is an operator in quantum theory? That's what I'm heading for, sort of a...
I mean, unless we're thinking about different experiments, I don't think what I'm picturing would lead to those conclusions, because you can describe two pulses interfering and showing interference fringes in time.
Not something. I want one pulse, like one particle, which is at two times at the same place.
One problem may arise that the pulse will have a frequency spread also.
Yeah.
No, but that is the point, right? Like, so because the pulse has a width, I think this is possible, that you can sort of turn it back and then...
Saying that you want to say the band splitting kind of thing in the energy.
Yeah, that is the thing that I'm not...
No.
Yeah.
But do you think what I'm saying makes sense physics-wise? I mean, asking for quantum interference in time, does that look reasonable to you? In the same spirit as the double slit experiment.
I mean, I think it's reasonable. I mean, but the way you would, like, you could take two pulse, but I guess everything I'm thinking of, you would somehow split the pulse in some additional mode, and then so you might have to couple to a spatial degree of freedom and then re-overlap them. So I don't know if that's the same spirit as what you want.
The double slit experiment, passing a particle through two spatially separated slits. Now you have to take one particle which is at one place but is experiencing two different times.
I mean, I think those I think those experiments can happen. For example, there's this idea, you're familiar with boson sampling, where you send single photons into different spatial modes and you look at spatial interference. There are many experiments which do the same thing but in time, where you have a single spatial mode and you have initially photons in superpositions of different, or maybe starting in discrete time bin modes, and then they go through some looped interferometer which loops those paths back, so then those two pulses will overlap, and then you can see like Hongo-Mandel interference in the time degree of freedom.
Okay.
So you can even do it with multi-photon experiments, at least in that sense.
Okay.
But he's talking about a single particle.
I mean, but if you can do it with multiple particles, you can do the same thing.
Yes,
So to put it slightly differently, what experiment would convince us that time is an operator in quantum theory?
I don't think these experiments I'm thinking of would, because everything I'm thinking of would be described by standard quantum mechanics.
I get what you...
So I have...
Okay, Manavan has a comment.
Yes, I have a comment. So just to answer what Professor Singh says, maybe my answer would be not directly to address what you have asked, but there may be some way you can address. So there is something called temporal Bell inequality, particularly the Bell inequality with respect to temporal orders. Yes, it's not the same thing, but if you consider your interference to be of some kind of superposition, and obviously that guarantees that whenever there is a Bell inequality violation, obviously this guarantees that there is some superposition. So this is the first, obviously, indirect answer. Another point what we have, I think is known, although I don't know in the context of causality what it will mean. that when I talk about quantum non-Markovian processes, it essentially says that some influence, possibly in the form of a memory coming from the past and influencing the present, no? So there are situations, possibly, when you superpose these non-Markovian evolutions, it may turn into Markovian one. And obviously you cannot explain them just by probabilistically mixing all the time. So possibly there can be, but I still don't know what what kind of implication it may have in the context of causality. Yeah.
Thanks, Manavendra.
No problem.
So I have a question for Manav. Why does this prove that time is an operator in quantum mechanics?
No. This has actually nothing to do with time to being operator. And we cannot have possible because energy is bounded from below.
Yeah. Okay.
That I can answer. That is not a problem. I think that's a myth, you see, that time cannot be an operator in quantum theory because maybe Pauli, so we will have something else playing the role of time. And that is the one that will deal with energy bound and etc. So if you have x, y, z, t, I'll bring in a tau that I described in my talk, call it Cohn's time or absolute time. That is the that becomes the ordinary time parameter, and we can apply Pauli's arguments to that fellow. But let this coordinate time t become an operator. That is not restricted by this kind of energy bound kind of. Otherwise, Stuckelberg came up with a relativistic quantum mechanics in which time is an operator, and then he has an auxiliary time. So that problem is not there. So like when we say a particle can be at 2 times at the same place, I have to they come up with some new time so that I can make these questions unambiguous. You see what I'm saying?
Yeah. I have just a comment to make. Historically, in 1932, Pauli's famous article in the Handbuch der Physik about quantum mechanics. In that article, he gave first the proof that why time cannot be operated in quantum mechanics. And in its proof, he used certain general assumptions. And one of them was the boundedness of Hamiltonian and those. So those assumptions, there is already this general proof that time cannot be an operator. Then one has to examine. So in that sense, operator may not be possible. But what has been in recent years more in the operational sense, the measurements of arrival time distribution and those questions have become important, tunneling time measurements. But particularly in the context tunneling time, people already have some understanding, those who follow the literature, maybe knowing this work of Steinberg and others, and the way they compute the tunneling time. But that is without using the operator notion for time. You can handle certain experiments involving measurement of time. One has to realize that all observables are not operator. A famous statement that Dirac made, he distinguished between observables and equal. So, like wavelength, you measure through fringe spacing. So in that sense, we say all measurements are position measurements. From there, we derive those quantities, and they are represented by operators. So I have two comments. First, one has to re-examine that Pauli general proof, which has been done by several authors, particularly in the context of interest in recent years in measurements of times in different contexts. And particularly in the context of arrival time, there is now a lot of debate going on, and several approaches have been proposed. And among them, there are approaches, and I think that is one due to Carlo Rovelli, the other, which uses some sort of operator for time. So if you can measure arrival time, there are claims that arrival time, and there are suggestions arrival time distribution you can measure, and you want to reproduce it from quantum formalism. That's the place where you need to handle time, and there, if it is necessary phenomenologically to treat time as operator, that is the avenue for further, and in fact, that is an important new area that may be opening up in the next. I wanted to anyway mention this, so there was no scope here, so I thought of bringing it up. because it is very instructive to read that original Pauli, which is never discussed in the textbooks, which should be. So I mentioned, and Pauli had a book also on quantum mechanics based on that article. So there are many things are there. Among them, this is the very important result. Now, in this current literature and studies on arrival time, very recently proposals have been made. Professor Winefoot may be knowing. Siddhant Das and others, they have come up with proposals how you can experimentally discriminate between these several, at least some of the proposals, but whether they're implementable or not, there is much debate. But anyway, what I'm saying that this is a new avenue that is opening up, and that approach, I think, is a very operationally meaningful approach for progress. That you need not, you just go on, how can you reproduce the correct arrival time, which can be experimentally verified. And there it may turn out that the approach which does necessarily requires time to treat time as an operator. So that could be a signature.
Thank you very much. But then you would agree that there will be interference.
And then one has to interpret. There I am worried that because interpreting interference phenomena, because interference occurs in various contexts. So here, interference in time, but that I have not yet understood if time is necessary as to treat as operator, for example, explaining arrival time distribution, how that proof of Pauli, which part, Hamiltonian people question that assumptions, and there are other subtle assumptions in that proof. So since there is already a general argument, of course, if we find specific example where it fails, we can do that, like in the von Neumann impossibility theorem. Right. Because the Bell example came up, people looked at what is wrong with that. So,
okay, thank you, Professor Hom. So next up is Sayan Chakravarti. Sayan Chakravarti.
Hi, I am Sayan Chakravarti, second year integrated PhD student at ISER Kolkata. So thanks both of you for the wonderful talk. So I have a question from Professor Sinha's, like not a question, like it is a query kind of thing. So in the end part of your talk, you have demonstrated like when you only get the experimental data in the deep of that thing, and after that, okay.
On what?
Which topic?
Deep of what? Deep in.
So in the fringes, you get the experiment.
You were saying that Hungerman.
Yeah.
But that was
and after, after that, you did the experiment in a larger area in open ground.
I think he's talking about the Boyd result.
Yeah.
The dip part.
Yes.
Yeah. So I think the only dip thing was the Boyd result.
Exactly. These slides.
Which one?
Okay. Here. And the next slide. Okay. So I do not understand the broadening in the violet. Oh, what's that? Does that mean? I do not understand.
Thank you for that question. I could not cover it because of the lack of time. I think we are sticking to the time. So what that blue band is, that is actually the theoretical expectation for kappa as a function of the detector's angular position. So of course what you see in the, can I get that pointer? Thanks, yeah. So, here you see the experimental result, right? And this comes with its error bar, which is of course the statistical error bar. But then comes the point that, if you just plot it using path integral or even FTDT, you will get a line as a theoretical expectation. But having said that, when you actually do an experiment, there are many sources of error which come into the experiment which are systematic errors. So these are just statistical errors, that is different. But systematic errors are something you cannot really do much about except account for them. And so in this particular experiment, if I recall, there were some 32 sources of systematic error. Essentially, when we say that we have these 3 slots, we say that, this is actually, it was made of a material which has perfect absorption for 6 gigahertz. But of course, how perfect is perfect? So you need to characterize that separately and figure out if there is any small deviation from that. Likewise, we are sitting in an open field There are many things which are going to bring in imperfections to the experiment. And so all those were also taken into account in the theoretical estimate, and the resultant graph that you see is essentially this theoretical estimation. So anything within that would be the value, because we cannot just have one straight line, because that is the error band, we call it. And so that is, so it's a very good question. And if you have a look at the paper which was referred to on the previous slide, then you can, of course, see that very detailed error analysis. That was a very important part of this paper. Yeah.
Thank you.
Thank you.
So would it be influenced by coherence also? Or?
Well, this was actually horn antennas. So we, of course, it was very good. Yeah.
Okay, thank you. So next is Anubhav Nandi.
Oh, hi, I'm a graduate student here at ISER. My question is for Lee, which I have already asked him during the break, but I would maybe reiterate it for the audience. Okay, so you talked about optical systems where the indefinite causal order and quantum switch came up, but are there solid state systems also where it can be realized? If you can shed some light.
Yeah, so there are other there have been implementations, I guess, in two other physical systems. So in NMR and using the IBM quantum computer. I actually forget if it was one of the online superconducting computers. But in the superconducting computers, you especially when you use the online platform, you enter a quantum circuit. So there they kind of explicitly have the extra gate uses in the experiments. But as I said, our experiments also have this loophole, or however you want to think about it, of these additional spatial modes. So those are the only other two platforms that I'm aware of.
Okay. Next is Gaurav Banerjee.
Good evening, everyone. My name is Gaurav Banerjee, and I'm a fourth-year student at ISER, Kolkata. Thank you to both of our professors for giving such a wonderful talk. I have questions, a single question for each one of them. So my first question is for Dr. Lee Rozema. My question is on the surreal trajectories that you were talking about. Could you kindly go to that slide, sir? The previous ones. Yeah, this will be fine. Yeah, thank you.
Yeah.
Sir, when you said you used weak measurements to find out this exact trajectories of the photons coming out of the two slits, when you pointed out that the trajectories do not intersect each other when we see for the two slits, but if you would consider a single slit, in case of a simple diffraction, we would have the photon going to the other part of the screen. But in the double slit experiment, the photon doesn't go to the other part of the bottom part of the screen, the photon coming from the top slit.
Yeah, according to the trajectories. Yes.
According to the trajectories. But then you showed in one more slide where where there is a crossing, where the trajectories do cross.
This?
Yeah, exactly.
Okay.
Yeah.
Yeah. Where was it? Yeah. So that was so you're asking why they're So the Bohmian trajectories don't cross. What this black line here? So these are just lines I drew on top of the actual trajectories that were weakly measured. This black line corresponds to situations where we're imagining now we have the switch path measurement. So we have a photon, which is a separate photon, which is entangled with the slit photon. Yeah. So what I'm imagining in this black line is a situation where we measure that extra photon, and that extra photon tells us that the photon went through this slit and not the lower slit. Yeah. And then there are situations where you can then later on measure the the photon in the slit, and you'll find it in the lower plane. And this black line is then kind of the resulting, say, quantum trajectory, or I don't know what the right word for it is, but it's the trajectory that, or I guess it's a surreal trajectory, where because the which way measurement said the photon was in this slit, but I found the photon over here, common sense would tell you that, you know, the trajectory should look something like this. But the Bohmian trajectories, or the weakly measured trajectories, are the ones down here, and then they correspond to something like this red line. So we have kind of a contradiction where the weak measurement, or the which way measurement, contradicts the Bohmian trajectory result.
When you do the which way measurement at the tip of the screen, at the end point,
then that's different.
That's a superposition of both the upper slit and the lower slit, right?
So in this case, I'm imagining that you're doing the which way measurement right after the slit, like when the slit photon is still here. If you perform the which way measurement kind of as a function of the second photon's propagation, then you find that the which way photon state actually evolves.
So we can't generally associate a single trajectory with a single which way result, right? So we get a series of which way results. So it's not well defined in that sense, right?
Sorry, can you rephrase that?
At each points of the trajectory, corresponding to the which way measurement, we are getting an answer.
Yeah.
Just at the beginning of the photon, when it is crossing a particular slit, it has a well-defined value, upper slit or lower slit.
Yeah.
At the end point, it's in a superposition state.
That's right.
So we can't really associate this entire trajectory with a single answer that the photon is from the upper slit or the down slit.
That's the interpretation that the Bohmians would suggest.
So in order to make it consistent with the Bohmian mechanics.
Yes.
Right? Okay, thank you.
I just want to make a comment. So this is with coupling with the momentum and polarization, right? And you are putting the Stokes vector. So there was a follow-up paper which interpreted as, in a classical way, as a pointing vector, through the pointing vector.
Yeah.
Does that work? Or?
So in some sense, yes. If you so the point is that these measurements here that I showed, which show these Bohmian trajectories, and I was saying there are weakly measured trajectories or Bohmian trajectories. They're also equivalent to, if I would just treat this whole field classically, and I were to measure the pointing vector as a function of the photon's position, you would get this result. So if you were to do the same thing in the case where you have the entanglement, it depends how you do the pointing vector measurement. So most measurements of pointing vector would be some classical measurement. And in that case, what you would do is you'd be essentially ignoring the which path photon, and the result would be this. You wouldn't see interference in the pointing vector. If you were able to measure the pointing vector on a single photon level, then you could recreate this, because you need to post-select this photon. Because there's entanglement, you need to post-select on this photon and then do your pointing vector measurement.
By placing, let's say, a probe particle or something like that.
With the pointing vector. Yeah, however you want to measure the. So I mean, you could also just say that our measurements are pointing vector measurements, and then you could do this measurement. So, yeah.
Thanks. You have another question?
Yeah, it's for.
Just before we go ahead, Professor Holm has a comment to make. So can you take the microphone? Can you bring that microphone? No, it's just because
of this whole question of Bohmian position measurement. We have Nicholas with us, and Nicholas has vowed to him not to speak today, but I would request him, because he makes some interesting points in that one of his recent articles on Bohmian position measurement, which I think are relevant to shedding light on the significance of surrealist trajectories. In fact, his observation that not all quantum measurements are measurements of Bohmian positions. And in that context, what all this means that has been discussed, I would be curious to know, and I know it will be instructive for the audience. So, Nicholas, please speak for once in this session.
Yeah, okay, thank you for forcing me. Yeah, I think Lee just said it. I mean, this is sold as Bohmian trajectories, but this is actually a totally standard quantum mechanical measurement. This is essentially measuring, okay, as you just said, the Poynting vector or the probability current that you find in any textbook. I mean, standard quantum mechanical textbooks. I think that the paper that I wrote, I think it was Why Bohmian Mechanics, I think is the title, no? I think it contains, it elaborates on an idea by Reinhard Werner and a co-author, forgot the name. So if you have, if you do Bell inequality with interferometers, or for instance we do, many people do, you know, the result will be the particle will either hit, let's say, the upper or the lower detector on Alice and on Bob's side. But you could also not put a detector there, just say because the particle is up or down, then that is a kind of result. And then I can undo my interferometric result by just closing the interferometer and just compensating for the phase. And then I'm ready to do a second measurement with the second input. So you have here something that looks like a local hidden variable model, and we know that this is not possible since it reproduces Bell inequality violation. And the trick here is indeed to these surrealistic trajectories that were mentioned also today. I forgot now, I think it was in the second talk, I'm not sure exactly. Anyway, it was mentioned. And this is maybe the way of thinking of it. Think of an interferometer, so you have a beam splitter, you have your photon going either up or down, and then you put two detectors, but detectors that react very slowly. And then the Bohmian mechanics has this very counterintuitive prediction that if the particle goes via the lower path, then, so it goes according to Bohmian mechanics to the lower path, then it is actually the detector in the other path that gets excited. And of course, vice versa, if the Bohmian particle goes the upper path, then it is the detector in the lower path that gets excited. There's nothing wrong in that, except that the value of Bohmian mechanics is the intuition of this, that these double slit trajectories. I think this is a nice, we have the feeling we gain some understanding, which is nice. But when you go to these Bohmian, these surrealistic trajectories, or this fact that you can have, okay, with Bell inequality also, when you realize that all these intuitive explanation and value of Bohmian mechanics gets completely destroyed. And so at the end, this is probably what Professor Holm wanted me to say. Don't trust the Bohmian mechanics too much, because in most cases, it gives you the wrong intuition.
Thank you, Professor Jisha. And yeah, so we move on. Next is Archana. Oh, you had, sorry, so you have another question.
I think you forgot.
Thank you, sir. So my next question is for ma'am. Once again, thank you for such a nice talk.
Thank you.
Ma'am, when you introduced photon anti-bunching, you gave two experiments. First one was using single photon, and the second one was using two photon sources. So when in the second experiment, when there were two photons being incident at the beam splitter, yeah, this one, thank you, sir. The reason that G20 becomes 0 is that the final state is a 2-0 state. My question was that, is it also possible that instead of the two photons simultaneously being incident at the beam splitter and going in a single detector, could the two photons still exist and both the photons simultaneously hit at the two detectors, and so thereby giving a non-zero value to G20?
So just a small correction, not a very small correction to the first part of your comment. First part not about me giving a good talk. That I am happy about that. But the first part of your actual comment, so I talked about anti-bunching, and this is actually photon bunching. So these are not two experiments for anti-bunching.
Oh, yes, sure.
Maybe it went too fast. So the anti-bunching experiment is about a single photon incident on a beam splitter. And of course, being a single photon, it will either go, either get transmitted or reflected. It cannot do both. And so if you have two detectors at the transmitted port and the reflected port, so only one of them will see some click, as we like to call it, and the other one won't. So if you do a correlation measurement, you will get a 0.
Sure.
And so that is the G2 0. So the G2 is this correlation function between intensity correlation function. It is the famous Hanbury-Brown twist interferometry experiment. The second experiment is actually the two-photon experiment, which is a bunching effect. It's not an anti-bunching. So there is a single photon incident on maybe, if you even play, I have a thing, right? So essentially this is the idea, right? So a single photon, when it is incident either this way or that way, so then of course, the idea behind, so this is the math, which of course I'm sure you're following. So when one comes this way and the other comes this way, then they tend to bunch, and that is the idea. They bunch, and so they form one state, which is 2, 0. So they go out together. So that is the idea of the photon bunching, which happens because of course, the bosonic nature of a photon. And so this is a bunching effect. But then I can see where the confusion can come, because ultimately, and this we were discussing in the tea break with some other people as well. So then here you have the 2 and the 0, or the 2 this side and the 0. So you're forming the 2, 0, minus 0, 2 state. And the minus comes because of the, the mirror giving a phase and so on, beam splitter reflection phase and all. But then what happens is that again you have these two detectors. So then one of the detectors will see these two photons appear. And of course, in our case, we are not even worried about number resolving detectors and so on. It is a detector which sees a click because of something being incident. The other one doesn't. Again, you're doing a correlation measurement, and if you have this, and we discussed a lot about the fact that they have to appear at the same time and so on, then you get this 0 for 0 time delay. So the thing is that ultimately we are measuring a dip in both cases, but from very different physical considerations. In the first one, you understand, in the first one, the single photon does not split. So it would be 1, 0, or 0, 1, whatever you want to call it, and so that gives you the 0. In the second case, two photons which are perfectly indistinguishable, they come out from the same port. And then again, it gives you the 2, 0. So,
so my point was that G20 need not necessarily say that the photons are anti-bunched. Even bunching can give G20. So
this is not a G20 measurement, because G2 is a intensity correlation.
So one of the detectors is still measuring 0 intensity, right?
Correct, but the other one actually has 2 of them. So in some sense,
so
it's
the correlation will still be 0, right?
Correlation will be 0, but then we don't traditionally call this a G2 measurement. Then it becomes a 2-photon interference measurement.
Okay. Thank you, ma'am. Thank you.
Thanks, Gaurav. Now next up is Archana. Here.
So I am Archana from ISER Mohali. Thank you for the very nice talks. So my question is to Dr. Lee. So you talked about these causally non-separable processes, and in the discussion of this OCB paper, they say that these causally non-separable processes that violate the causal inequality will be applicable in the regime where quantum gravity is applicable, or there is a superposition of space-time metric, whatever that means. And then in some other literature, they say that quantum switch is a time delocalized process, and whatever that means. So can you make some comments as an experimentalist? What do you think when you hear the phrases time delocalized process, or the regime where a superposition of this space-time metric is applicable?
Yeah, so to the first point, the superposition of space-time metrics, and I think this is so I think this kind of relates back to what I was saying about there may be extra assumptions that go beyond, or that that we don't know the form of the thing, the process that connects the two labs. In that paper, they just kind of speculate that there might be physical processes out there which can lead to these effects. And one thing they say is this superposition of space-time metrics, which they propose, and the idea there is, you have some mass that you put in a superposition, or you have some mass which will lead to some metric, and now if you have the mass here, you get one metric. If it's there, you get another metric. If you put the mass in a superposition, then you have a superposition of metrics. And they're kind of proposing that we might need to look for, if we want to see violations of these inequalities, we might need to look into situations where we have masses in superposition to violate these inequalities. So kind of bring in gravity-like effects. So that's the first point. The second point on the time delocalized processes. So people in this community, people can mean different things when they say that, but the general point people are trying to make is that when the maybe I have it here. So we have this space-time diagram for my experiment, or these experiments, where we have in one branch we have the photon going towards U1 first and then over to U2, which leads to these two space-time points. And in the other case, we have it going to U2 and then to U1, leading to those two space-time points. So when people talk about time delocalized processes, they kind of mean the fact that these two things are occurring in superposition. So you have a superposition of these different space-time events.
So delocalization means this superposition of time.
Yeah. Yeah, I mean, I think it's kind of related to the idea that when you have a quantum particle in a superposition of times, which all particles we make in the lab are, it's impossible to really make a photon exist at a specific time. It always has some finite coherence length. So another way of thinking about it, another context people use it in is when you have these sorts of states where you have a quantum particle in a superposition of arrival times, and I want to say, now I'm going to send this photon, through a given optical element that goes through a wave plate, and I want to define the event as being a photon passing through that wave plate. But we know that the photon exists in a superposition of times, so then you kind of have to think about the photon passing through the wave plate as a time delocalized process.
Okay, thank you. Yeah. Thank you very much.
Yeah. Thanks. So next is Giris. Yeah. Please bring your microphone here.
Yeah, hi. I have two general questions on weak measurements and weak values. I've tried to understand this before, but never really got around to. Is there something really intrinsically quantum about weak measurements, or do they also apply to classical fields? Because although you write it in this ket notation, it seems to me that if you take a classical light field and pass it through calcite crystal,
100%.
Yeah, you just put a polarizer, pre-select the state to H, and then post-select the output state to maybe something very close to V, you'll probably get something like the weak value, right?
You get in 95%, maybe probably even more of the weak measurement experiments that have been done, it's single photons, because in this trajectory measurements I was talking about, it's only one photon, and I'm coupling the momentum of that photon to its polarization. So the experiments were done with single photons. In one case, it was photons generated from quantum dots. In another case, it was with photons generated from down conversion. But if I were to send a classical light, just a laser through the experiment, I would get exactly the same result.
Okay.
And I think it's also related to what we were discussing earlier when we were saying that these measurements of the trajectories are equivalent to measuring the pointing vector, which isn't a quantum concept. This is just from classical electromagnetism.
Right. Yeah, I just wanted to add that actually, I wanted to add on your behalf that Professor Nirmalya Ghosh has a beautiful lab here in IISER Kolkata, and their main thing is doing weak measurements using classical light.
Oh, I see.
So, I mean, in fact, he can answer all the questions on what all is possible using classical.
I think Lee also shown,
I mean,
of
of course,
tell you one thing,
yeah.
that when you do weak coupling between 2 degrees of freedom of, let's say, photon or light, then actually it can be produced by classical light also.
I see.
But you were showing an example where there is a weak coupling between 2 systems, it's through nonlinear effect. So that is a true non-local weak measurement.
So
that
just before I give it to Lee, so one point is that, I think the experiment that you're doing, where the interpretation of the experiment will change, depending on whether you're using classical light or a single photon.
Way, let's say whether you do a classical light or a single photon, so if you couple between 2 degrees of photon, freedom of the same light, then of course there is no question of non-locality there.
Correct. But then if you think about Cheshire Cat.
Experiment where using this nonlinear coupling between 2 systems.
No, but then if you think about the quantum Cheshire Cat.
Yeah, so there.
So a single photon, and of course it's polar, projection weak value in one arm and the polarization component in the other arm. When if you can of course do the same experiment with using laser also, but that doesn't mean the same thing.
No,
you're not separating properties of the same particle.
It's a classical analog.
Classical analog. That's it.
But I'm saying that there is something which is non-local weak measurement that cannot be done even by a classical analog. That is what I wanted to mean.
There's a comment there. Maybe as the microphone gets to Nicholas, I can say. I'll just quickly say, I don't know all of the experiments that have coupled 2 different systems, but this paper here from Ephraim Steinberg's group, this weak value amplification of the nonlinear effect. In this experiment, they really had 2 separate beams. I think they were actually coherent states, but they were interacting, or at least one of the beams was a coherent state. But they had 2 separate beams which are using a nonlinear interaction. So there the weak value was at least written onto a different particle, and I don't think you would get the same result if you did the classical treatment there.
Yeah, exactly, that's what I wanted to mean.
I see, I see.
And there's maybe been a handful of other experiments, but.
Okay.
Yeah, if I may, just a comment on that. I think it's a beautiful idea of what yesterday I called good physics, because the concept of weak value is really coming and was motivated by basic quantum mechanics, but it has applications, for instance, in classical optical communication, so the standard thing that we are all using with optical fibers and bright laser pulses with millions or billions of photons per pulses. And in these optical systems, you have a bit of polarization mode dispersion, so one mode goes a bit faster than the other one, and you also have a bit of polarization dependent losses. And of course we post-select, the post-selection in this case is very natural. We post-selected those photons that make it to the detector. Those that get lost by the polarization dependent losses, they are naturally disregarded, they have to be disregarded. And indeed the people in classical optical communication have noticed what they called abnormal polarization mode dispersion. So they know that they have some dispersion, but what they measure is larger than what they expect. And the reason is exactly because of the natural post-selection they're doing. They're actually measuring a weak value. But of course they didn't know that they're measuring a weak value. But I think it's a nice example where this deep quantum concept feeds back into very, let's say, engineering-like physics.
Yes, Manolendra has a comment to make.
Thank you.
So I think Professor
Thank you for the answer. But I think I still miss something. So first thing is that for this weak value to appear, you need to have measurement-induced collapse, right? You have to have a projective measurement, right?
I mean, there's a projective measurement, but in most of the experiments, the projective measurement doesn't happen until the end. Like in the example that Nicholas gave, the projective measurement is, I guess, the photon making it through the fiber.
So correct. So that means, although you are saying that this is a classical light, but it's actually operating through this quantum mechanism somewhere, right?
But there's no non-local effect when the post-selection is done in the same particle, right?
So
because
that is the point, that if you use 2 degrees of freedom of the same light, so there is actually, you can also interpret it purely from classical electrodynamic theory.
Okay. Okay, I still have to digest this, but on the other hand, I know that this the real part of this weak value has something to do with position displacement of the meter, and the other one is for the momentum. In this particular case, how do you interpret it? For classical, is it the same?
Yeah, so you can use different pointers. For example, if you use polarization as a pointer, different element of the Stokes vector will correspond to real and imaginary path order weak value. In the experiment that Lee was showing, where they measured the trajectories through weak value by reading it from the polarization as a pointer, their different Stokes vector served as the real and the imaginary part. They are like conjugate spaces.
Okay. Thank you.
Yeah, when you do these measurements, these experiments like are done in this paper, then there are two separate probes, and there can be some collapse that's induced, but maybe non-local. But
thanks. So next, Professor Weinfelder wants to make a comment.
Yeah, I mean, more than 100 years ago, Walker tried to make single photon experiments by attenuating light, and he didn't see a difference. And then Glauber told us that as long as we just do experiments with a single particle, then that can be equally well explained with lots of particles. So as long as we only detect one particle, and I would even make it more strong, I mean, it's 1 minus epsilon of experiments which dealt with single particle detection or single, just with intensity measurements.
Yeah.
And then you don't see any difference.
Right. Thank you. So we have next up is Saurabh. Saurabh.
Hello. Yeah. So I'm Saurabh. I'm a PhD student here. My question's for Dr. Rozema. So you talked about the quantum switch, and so there's this line there that this can't be. I think it's a bit before this, like at the beginning of the talk, maybe. About how this cannot be done by a quantum circuit. So.
Yeah. I think this one.
So this thing, so in the next page, you have written the action of whatever this does, in terms of like, there are two orthogonal vectors, and that maps to two different orthogonal vectors, right?
Yeah.
So basically there's an infinite number of unitaries which would do this, right? Because you're just, and so if you have any one unitary, then you could write a quantum circuit which would do exactly this.
Yeah, so you can write a quantum circuit to get the same evolution, but it will require multiple uses of the gates. So that statement I made back there is in the context where we only have one gate U and one gate U2. If you're allowed to use the gates multiple times, you can write a quantum circuit that does everything.
No, that circuit would just have to be run once, but you are saying that there will be multiple instances of U1 and U2 within that decomposition.
Yeah.
Right? And
Yes, that's right.
Okay. Now, but there's so much freedom, right? There's like, we are specifying just 2 dimensions of a 4x4 matrix. So won't there be some, I mean, I guess maybe in your paper you prove this, that there is none of the decompositions have.
This paper by Giulio Kiribella proves this idea.
Okay, I'll check it. Thanks.
Yeah.
Thank you. So any other questions or comments? Okay, please. Please introduce yourself. And
yeah, I am Orgho Das from IMSC Chennai. So again, this might be a very naive question, but anyway, I am placing it. More of a confusion. So this is the chapter 1. I mean this anti-munching, when a single photon is passing through this beam splitter. So it is entangled into 2 different paths, right? I mean, so I am confused in the fact that one path is from reflection at the beam splitter, one is transmission through the beam splitter. So these individual events will have different effect on the beam splitter itself, right? So in that sense, this path entanglement should introduce maybe very tiny, but entanglement in the beam splitter also. And then I'm thinking that beam splitter is a macroscopic object, so it should decohere or maybe collapse very soon, maybe in a macrosecond. So why it is not reflected? I mean, this beam splitter and path states should also entangle in some sense, but beam splitter should collapse to a classical state very soon, in microseconds or so, as it was being discussed.
I think I understand.
So, yeah.
So you're essentially saying that when the photon transmits, maybe it doesn't impart momentum to the beam splitter, and when it reflects, it kicks the beam splitter in some direction, so there should be entanglement. In principle, you're correct, but that momentum the photon gives to the beam splitter is tiny. So actually similar to this weak measurement idea, there's really no real entanglement generated because the momentum kick is so small that it doesn't lead to any measurable entanglement.
Can I add something to that? So I think this is also reminiscent of this Einstein's back action principle. So when you have this single particle incident on a double slit, then does this actually impart some momentum to the slit? And by doing that, are you able to gain some information about what is happening in this interference? And so, it's the same sort of whatever Lee said is exactly that calculation has actually been done. For the double slit scenario. I don't know whether it's been done, but the beam splitter and double slit, Mach-Zehnder is a double slit interference. So, the Mach-Zehnder is an analogous experiment to a double slit experiment. So, in some sense, the double slit calculation has been done, and it has been shown exactly what he's saying, that it is such a tiny effect that, you won't really see any ramifications in a macroscopic measurement. But then you can look up that paper, and a priori that reference is not coming to my mind, but maybe I can share it with you once I look it up again. But then this has been done, this calculation has been done. But then and it should hold for the beam splitter scenario as well. Yeah.
Thanks.
Okay, yeah. So
momentum key.
Just 1 second.
Yeah, my name is Prem. I'm from IMSC Chennai. My question is to.
Portable. Just 1 second. So maybe hold on. Professor Home has a comment to make. No, then you can just make a comment.
Related to the momentum kick, in fact, there has been interesting series of studies in the 90s by this Englert group and PA on relating the momentum kick to what extent it washes out the which part distinguishability.
But do you remember the reference?
Reference, this one can look up. It's the Englert paper. Englert paper. Hello. There has been a series of papers in the 90s, I think, 80s. He's the man. Do you remember? Do you remember those studies on double slit? No, I can't. No. Do you remember those papers which discuss these Welcher-Wake experiments, the kind of momentum kick and to what extent they wash out the interference, those relations? In fact, there has been an interesting line of studies, where because you have which part distinguishability and which part distinguishability through momentum kicks and the interfere to what extent the visibility is.
And this has been done with proper math. That's what I'm trying to say.
And there has been debate also about these calculations in nature and so on.
So now I think you have enough clues to do the light Google search. We've forgotten the right reference.
Englert is surely.
Would you, so you want to make a quick question because we want to close now?
No.
You can always continue the discussion in the dinner.
No. It was in 90s. No, all those papers, Welcher-Wake determination, to what extent? Yes. So you start you gather the clues of the names of the authors. That was very interesting line where you derive quantitative relation on the which part distinct complement. And the genesis of all this lies in the Solvay conference. Professor Banerjee will be happy because he wants this to be. In the 1927 Solvay conference, this was first raised when the board stated its complementarity. Then this issue of momentum kick was pointed out by Einstein, but really the rigorous thing was done.
So one last question we'll take and then we will break. So quick question.
Yeah, so my question. My name is Prem. I am from IMSC Chennai. My question is to Urbasi ma'am. You mentioned that HOM experiment can be demonstrated with classical light also. Is it because of indistinguishability of the light? And if so, is it not inherently a quantum feature?
Yes. No. No, yeah. So the whole point was that the HOM, so we call it the HOM-like dip. So we are not going to say that it is a Hongo-Mandel interference because that has a specific meaning, right? Which is to do with indistinguishable photons and how well you can, resolve that. And the whole experiment from Hongo-Mandel was in that genre of reducing that time gap to sub-picosecond and so on. But what we can do is by using classical light and phase control, and I told you what phase relationship, so uniformly choosing between 0 and pi as the phase relationship, we can actually have this same correlation measurement done, and we can see 100% visibility for the dip. So if you just do this measurement and don't know what is your source, then you will not know what is the genesis of this measurement. Whether it is two indistinguishable particles, it need not be photons also. Hongo-Mandel experiment is done in other particles as well. But then two indistinguishable particles, or is it just that you have done this perfect phase control between two classical pulses even. So that is the thing about fooling the observer, that by just looking at the measurement, I'm not able to say whether I had a quantum source or a classical one. So we need to go one step extra and do an interference experiment to figure that out. We are not saying that the classical results happen because of indistinguishability. The classical results happen because of this perfect phase control.
Okay,
Yeah,
thank you.
Okay, thank you. Now I think we have to close the session. I would of course like to thank both the speakers for stimulating such discussions. It has been wonderful, 1.5 hours almost we have been discussing, and still I think everybody here wants to discuss further, and we will continue the discussion in dinner, I think. So let's again thank Lee and it's also my recent duty to hand over this memento to Lee and Urbasi. Yes.